I should start with a few disclaimers. Amongst those changes that I have done for today is not just to make it shorter, but also because, as you probably realized, the pre-recorded lecture that covers the topics that I will mention today in a little bit more detail in relation to the coursework was released only this morning. So I'm not expecting you to have watched it already, but I have, however, modified that pre-recorded lecture accordingly to be very much a light touch lecture. It doesn't have a lot of quantitative stuff, meaning that is a little bit long, but very much qualitative, just to give you quite a bit of background of the few issues that you have to think about when you do offshore foundation design, which is the topic of the next two lectures. Having done that, I recommend that you do please watch that lecture for certain before next week. And what we'll do next week is that we are going to jump straight away into the more quantitative aspect. As you'll hear in the lecture, I'll focus on the ICP design method for piles as the key foundation structure that you deal with in most of the offshore developments that you might be involved. So having an understanding of how those design approaches work will really help you in the limited time that I'm to only the easiest one. You can also get an understanding of the other methods that are used in different parts of the world for the same purpose, because they are all similar. The other warning that I will want to make, and that I will remind you by announcement or email on Moodle next week, is that I have to start the live session next week slightly later than usual. Around, I think we have to start at 4:30 instead of 3, and the reason for that is that unfortunately I have to chair a session on an international conference, and of course that cannot be changed in terms of timetable. And I'm due to do that until between 3 and 4:14. So by saying that I'll see you at 4:30 next week gives me 15 minutes to get everything ready before you join in. So yes, bear that in mind. We'll start 4:30. As usual, I will try to give most of the theory of the lecture on a pre-recorded lecture, which, being more quantitative, will have to, you'll probably will take longer to digest. So my aim is to have it ready by the end of the week, meaning Friday or maybe over the weekend, so you have at least the whole of Monday to watch it before the Tuesday session at 4:30. But yeah, having said that, and giving you apologies for all those last minute changes, I'll start showing you a few things of what is then to come and extend a little bit that pre-recorded lecture, or give you a sense of what it entails by a short recap just now, and then I'll follow that with some comments on the coursework. You'll finish the session today knowing all the details of the second coursework submission, which of course is related to these two lectures that we are starting today. But yeah, in the pre-recorded lecture that you may or not have seen, I say that when you are dealing with offshore development, you obviously have to do a site investigation, and that is relatively similar to what you do for onshore developments, in the sense that you obviously start with a desk study, that gathers as much information as you possibly can about the site. And that includes, particularly if you are dealing with wind farm developments or oil and gas structures, you obviously need some meteorological and oceanographic data to be able to estimate things like extreme wave heights that derive on wave forces, magnitudes of wind and their directions across the year, so you can again estimate representative or significant wind magnitudes for the design of those structures. What you then normally will do, and having an idea of what to expect, is you will send offshore as part of the site investigation some form of vessel or ship that simultaneously will do a geophysical investigation and a geotechnical investigation. The geophysical investigation is mainly to give you an idea of the stratigraphy of the area in a very quick manner and over a large area. That's why we use geophysics, because it's simply a sensor that can be dragged by the vessel as it moves, and it will capture by different sensing techniques, refraction and diffraction or other methods, the layers that may be at the bottom of underneath the bottom of the sea surface. But at the same time, either as part of the same vessel or a different one, you'll have an actual site investigation, quite similar what would you do in the onshore developments, but of course with more sophisticated equipment because it's on offshore. But the idea with that one is that you both do in situ testing and you also take some samples for laboratory testing. The design method that I'm going to explain to you tomorrow, sorry, not tomorrow, but next week, is based mainly on the Cpt Test results that you will get from such geotechnical site investigation. You have or should have some idea of what a Cpt test, because I did mention it in previous courses. If not, that's what I'm going to do later on. Describe a little bit of what it consists of and what you get from it, because again, it's the basis of most current offshore design methods for foundations. So it becomes the basis of everything we're going to do next week, that little image, which is a Cpt test result. So there we go. So the other thing that I go a little bit on detail in the pre-recorded lecture is that your foundation type depends, of course, on site conditions and environmental loads, as well as the mechanical components that you may have, for example, on a wind turbine, as John's here. But the biggest determinant that enables you to choose the type of structure is the sea depth. And what this very nice illustration shows you is that if you're at shallow depths, you can use what we call a monopile as a foundation. But as you go deeper, because the environmental loads become much more significant, then you need jacket or tripod structures like the yellow steel structure that is being shown there. And those may be founded also on individual piles, each of those extremities or legs of that jacket structure. If you continue to go down, you may have what we call the tension leg platform, which is essentially a floating structure which is supported by tension cables, which are then anchored or joined to smaller piles of different types, which are also discussed qualitatively with some detail in the lecture. But if you go deeper, you have more catenary style risers that are anchored to the seafloor via different anchor types, which are also shown in the lecture. But what this image also shows you is that at least for 50% of these structural types, we use pile design. And the key here is that these piles are not the same as the ones that you are used to on an onshore development. In an onshore development, a pile has typically something between 40, and if you are involved in something really big, you may have piles of maybe 1 meter diameter and up to 30 diameters depth. 30 meters depth or something like that. Speaking of offshore piles like these ones, particularly in this region to the left of the diagram, you are speaking of piles that can have up to 20 meters diameter, and the depth can be equivalent to that of onshore piles. So what that gives you is an idea that while onshore piles might be much more elongated, offshore piles are much more short. To do that design that applies to at least these three types of structure, and for certain anchors in those two larger floating structures on the right. Again, to compare two things that you do onshore compared to offshore, a typical onshore wind turbine will have axial loads of maybe 1 meganewton, 1,000 kilonewtons or something like that, due to structural loads, which is what this is representing here. A shallow surface wind turbine, because of the size of the things that you are dealing with, which I discuss also in some details in the lecture, you are talking about something that could be of the order of 6,000 kilonewtons, 6 kilonewtons, up to 10 kilonewtons with the bigger components that are being recently developed. Wind forces, like the ones indicated, the wave loading ranges. But of course, that's why we do things offshore nowadays a bit more, because we can get more benefit from bigger magnitudes of wind. If you're talking of larger structures that may be used not just for the site investigation, but for the construction of oil and gas extraction platforms or other related structures, that vertical load can be increased up to 200 meganewtons. And again, because of the simple difference in scale, your lateral load will also increase. So the point to make here is that, yes, you are in a completely different set of figures, much larger things, which obviously derive in much more significant cost. I also mentioned some figures regarding what will cost just the hire of one of those technical vessels that you will need just for the site investigation, and that is cheaper compared to the ones that you will need for the actual driving of the piles. I do spend also some time highlighting in the lecture that you are not only dealing with environmental loads like the waves and the wind loads, in addition to the structural loads, which I was just mentioning, but you have to deal also with these two dynamic loads, one which results from the rotor frequency, the engine that is just there, which we call the 1P frequency, but also with the blade passive frequency, which results from the movement of the blades themselves. And those have different frequencies on a magnitude or 2 or 3 times the one that you get in the rotor, and that's why it's called 3P, because it's basically a factor of the number of blades that you have, and in a typical wind turbine you have 3 blades, so that frequency will be 3 times the one of the rotor for design purposes. The significance of those frequencies is quite high, because as you know from what you learned with Juan, you are very interested on the dynamic response of the soil, and in particular on the damping of that soil and its natural frequency. And as you can imagine, this is a relatively complicated soil structure interaction problem, in which the key aspect that you have to verify with regards to these two mechanical frequencies, let's call them like that, is that those frequencies must not coincide with the natural frequency of the foundation soil, because of course your system will start to resonate and collapse structurally speaking, and that's something that you need to avoid. So there are certain aspects that you need to be quite careful about, and I will discuss that in a little bit more detail next week as well, but I wanted to give you the background. The other thing that I speak about is that as you had extending static things to earthquake or seismic designs in retaining walls or slopes, what happens between onshore and offshore design of piles is also an extension of what happens onshore. That extension, what it means is that for offshore piles, you still will do calculations of total pile capacity being the sum of base capacity at the bottom of the pile and shaft capacity along the perimeter of the piles that you design. But while will depend on things like the alpha coefficient and the undrained shear strength and bearing capacity tiers at the base, as we did in previous courses. These most modern methods of design, including ICP, which I will show you in detail next week, do these calculations on the basis of Cpt tests rather than in measurements of shear strength parameters. And that's what we will be focusing about. It's not to say that methods like these are not used offshore. They are part of the American Petroleum Institute standards that are still used in North America. But it is well recognized by industry at the moment that such designs based on that type of standard produce very expensive designs that are very conservative, which yes, it's good that they are conservative because they are safe. But one point that you must always keep in mind is that any saving that you can make in a pile design equals a lot of money. Think of, again, renting one of these sophisticated vessels at £1 million an hour. Think of a wind farm that may have something between 75 to 200 wind turbines, and imagine that each of those is founded on a monopile. So you have to build up to 200 monopiles offshore, each of them to a depth of maybe 20 meters. And assuming that everything goes well, you will spend maybe 1 hour per meter of penetration. if you can reduce your design to be able to afford a pile with a meter less of depth, and you're saving that times 200 piles on that just simple saving, you are just making a saving of 200 million pounds. So that's why these methods are becoming more used, because they give increased reliability, because they are based on things that we have now much more experience. And those things that we have much more experience are, in particular, the Cpt test, which is essentially a tube with a conical tip that I'm showing here in section. And the idea of the test is that as you penetrate it into the ground from your source, also charging you per time, you can measure the tip resistance, but also the distance. Quite similar to what your pile capacity is related to the tip resistance, and you also measure shaft capacity related to the sleeve resistance on the sides. In addition to that, you have other sensors, for example, the friction ratio, which as a standard you get from most commercial companies. And the reason you get that is that the combination of those two parameters is actually quite useful, not just to identify soil types that you then confirm with the actual samples that you get from limited positions close to that prospection point, but yes, you can see that, for example, friction against resistance, or in other words, the slope of that line, which is equal to the friction ratio, gives you a good indication of the type of soil you are dealing with. Not only that, those parameters, we have now so much empirical evidence from previous projects that they correlate reasonably well with other soil properties. And that is what you will be doing from next week and with the coursework. I want to chapter 4 that gives you some of those empirical relationships of equations between the Cpt test results and geotechnical properties like undrained shear strength or shear angle of shearing resistance that you then need as an input for the design methods that I'll show you next week. There are other references that are quite useful, and those include this one, Con Penetration Testing in Geotechnical Practice by Loon and co-workers. This is practically the industry and one table of contents. actually coarse grain soils like sands and so on. So when you go to these different pages, you can find different equations. And again, I'll show you some of these next week. But the rationale, what I'm showing you is that we have so much experience on CPT test results that you find quite a lot of these relationships. And the biggest challenge nowadays is not really about the design method itself. You'll see next week that actually that is quite straightforward. It's a standard recipe. But what is really difficult is to decide which relationship do you use between CPT test data or results and the properties that you need to input in the design. That's the most difficult challenge, because you need to make sure that the equation that you use is appropriate to the problem that you are considering and that is actually applicable, because many of the empirical relationships are applicable for different sites and so on. So that's what we will discuss again with some detail next week in the live session, but also in the pre-recorded lecture when I explain the method. And I'll highlight some of these examples. But what you will also see in Moodle later on is that your formal coursework brief is now ready. So you have your coursework, as I'm showing you here in the screen, with the first question that I showed you a few weeks back, which is really easy. Then the second question that I gave you last week, which is also relatively straightforward, but a little bit more onerous than the first one. And then the last one, which as you can see is simply the design of a pile with a load of 8,000 kilonewtons or 8 meganewtons, assuming that you have a water depth in the ocean of 30 meters from the water surface to the seabed. And you'll have some data on Moodle. So what you'll get on Moodle? CPT test results in terms of tip resistance and friction resistance, which correspond to McDonald's fire. But the idea is that from much deeper layer of normally consolidated clayey silt again. What that means is that you will have to deal with design methods for both sand and clays depending on the pile design that you choose to do. And that is the extract of the site there. So essentially what you have here as information is your desk study and part of the site investigation for a real project. And I'm telling you, design the foundation of one wind turbine for axial capacity, not for wind loads or anything like that, just for axial capacity, which makes calculations less onerous, but by no means not challenging. So that's why you see in the coursework that actually that counts for 32% of the course, which is quite a lot, because you'll have to not only do calculations, but also justify why did you choose certain empirical relationship between the CPT test and the soil properties and so on. So that is what is going to be available on Moodle during the course of the week, but you now have an indication of what you need to do. So once again, my recommendation is that if you haven't done questions 1 and 2, this is actually a good time to do it between now and next week, so you can focus on the third question the rest of the time. And that is strongly advisable because, again, question 1 and 2 are actually quite easy, and you can do them without having to reread the material a lot if you start now. But if you leave it to the end, it will become a little bit more challenging because you'll have to remember everything that I have said. If you can then focus only on question 3, again, by the end of the lecture next week, you will be able to do that relatively quicker. And the quicker you do it, the better, because you'll remember everything. But if you can't, remember that we have given you plenty of flexibility for the submission deadline of that. That is just a latest, but if you want to submit it before, you can. The internet hasn't interrupted, luckily, but that's all I wanted to tell you for today. Just emphasize the message. Please keep an eye on Moodle because I'm going to explain the design method principles in advance so we can focus on the actual calculations in the live session that will start at 4:30. And I wanted to show the coursework in advance so you also have an idea of how important that lecture next week will be. We probably have 5 or 10 minutes for any questions that you may want to ask before they cut off the internet service here, as I mentioned at the start. So if you do, please fire away now. I'll stop showing the screen and being able to look at the chat. But if you don't want to write on the chat that you want to ask, by all means, just unmute yourself and ask the question.
Okay, thank you, Daniel.
No problem.
I have a question.
Yeah, of course. Go ahead.
Yeah, so let's say that you have a shallow water table, like around 10 meters.
Is it starting?
And then the soil is like around 5 meters clear or silty. And then it's say it's sandstone. And let's say we want to drive piles into the sandstone, we want to use driven piles. So what is the procedure for that? Do we go until we reach the rock, or do we go even more in the rock, like let's say half a meter or more?
Yeah, so...
Do you know how it usually is?
Yeah, what you will normally expect, particularly onshore, is not wanting to go that deep and not touching the sandstone because the construction process will be quite difficult and very costly. So what you would try and aim is to either reduce the pile depth by increasing the diameter so you can build it quicker. And or the other option is that you use something like suction caisson, which I mentioned briefly on the pre-recorded lecture, but that we will not discuss in much detail here in the course. But by all means, we can discuss in more detail next week if we have the time. Any other questions?
Okay. So just when the rock is concerned, you want to avoid touching the rock with the pile because it's cost.
Yeah.
Is that what you said?
Sorry, what I call here was that if you want to avoid the rock because of cost as the main reason, yes, the answer to that is yes. But the yeah.
Okay, thank you.
Yeah. Anything else, guys?
Okay, thank you.
Yeah.
Oh yeah, one more.
Okay. Somebody is asking, so let him finish first.
Yeah. It seems there was no, so go ahead, Gopta, ask your question.
Okay, so I want to know, as you said in this lecture earlier, that we are checking our file only for the axial load, not for the dynamic loads like wind load and other like sea load. So, is there any specific reason behind that, or we do these kind of checks later? Mean to say, we design our file for separately,
Yeah.
or what?
Yeah, good question, and I shall clarify. It's not that we don't look at the lateral load on a real pile design. We do look, but the reason we are emphasizing on axial load is to essentially make the coursework slightly easier. That doesn't mean that we don't look at the other loads. I will discuss them on the lecture of next.
Okay. It's just for the coursework part.
Yeah,
But
just for the coursework, but the lecture will cover all those loads, so don't worry. I'll show you how to deal with them next week as well.
Right.
Anything else, guys?
Thank you, Daniel.
No problem. Thank you for asking as well. Good to clarify. So, yeah, I'll see you guys next week. Good that I could say goodbye before the internet is cut. But yeah, I'll make a reminder. Remember, it will start at 4:30 next week. Bye-bye.
Bye-bye.
Thank you. Bye.
Yes, thanks.
Bye.